Hi, I'm Clay Thomas, and this is classification of priorities such that deferred acceptance is OSP implementable. So peeking ahead in the talk a little bit, the core question to keep in mind throughout this whole talk is when is the strategy proofness of stable matching mechanisms like deferred acceptance, when is this easy to see? All right, now slowly introducing the setting and everything, we're studying matching mechanisms, say with n agents trying to match to n positions, where the agents have a strict preference list over all of the different positions, what they like best, second best, third best, and so on. One very basic matching mechanism you could use is called serial dictatorship. In some fixed order I equals 1 to n, call up agent I and have them pick and permanently match to their favorite remaining position. And this is pretty basic, but we're gonna kind of use this as a baseline throughout the talk. Things get a little more complicated when the positions have priorities over the agents. For one running example to think of, say students are being matched to schools as the positions, and students that live very close to a school have an advantage. They have a high priority to get into that school. And note that we call them priorities because they're fixed and they're non-strategic. That's the only real difference between preferences. And we're looking for a stable matching where no pair of an agent and a position would like to get up and depart their assigned matching and match to each other instead. The canonical way to find a stable matching is this deferred acceptance or Gale-Shapley algorithm, in which agents propose in order of their preference list, and the positions tentatively accept the highest priority proposal that they receive over the course of this process. And both SD and DA are strategy proof, which is just the definition we're probably all familiar with, which is regardless of what the other players are doing, I do best by reporting my true preference list over the positions. But the question we're asking is how easy is it to see that these mechanisms are strategy proof? And here we have a really dramatic contrast. To mathematically prove that SD is strategy proof, it's basically just one line. Because here, truth-telling means pick your favorite remaining thing. And if you picked anything else, well, that would definitely be bad for you. DA, on the other hand, this is a legitimately complicated mathematical fact to prove that this is strategy proof. And field experience trying to teach this proof to undergrads indicates that indeed people have a bit of difficulty getting a handle on this. Never mind all of the experimental papers that find that agents lie in DA mechanisms in practice. So what's going on here? Can we formalize something behind this contrast? So the definition of strategy proofness really requires contingency reasoning over the reports of the other players, the pref minus I of what players other than I are doing. The contingency reasoning says for all pref minus I need to check that the best I can do is reporting my true list. And I have to hold this pref minus I constant when I'm comparing the truth to the possible deviation. And this abstract math proof for DA must implicitly handle all possible pref minus I's at once. Technically, the proof for serial dictatorship does this as well. Because if I change pref minus I, well, in the first instance, the first player might take my favorite item. And then in pref minus I prime, they might leave it and I'll get a chance to get it. So if I don't do this contingency reasoning, holding things constant, indeed, I won't be able to see strategy proofness, even in serial dictatorship. But when agent I is actually called to act in serial dictatorship, no contingency reasoning is needed. At each node where they act, deviating from truth-telling instantly and permanently harms them. So formalizing this observation leads you to Lee's seminal 2017 definition of obvious strategy proofness, this type of strategy proofness that is easy to see. The definition is that every time in the mechanism where I act, the worst thing that can happen if I tell the truth for the rest of the game, the min over other player strategies, this is at least as good for me as the best thing that can happen if I deviate right now and take some action other than the truth-telling action. So when I actually proceed to act, no contingency reasoning is required. That is, if I am considering deviating to the action taken by some pref I prime, I can see that even if kind of the whole world conspires against me, I'll still rather take my truth-telling action. And that's kind of the catchiest way to just remember this formal definition. You believe the whole world is conspiring against you, but still you want to tell the truth. So this definition has really caught on in the last several years. It's really this fundamental notion for what strategy proofness you can verify only based on your possible experiences of the game and not understanding how other players' actions determine your outcome. And it applies automatically to several interesting settings like ascending implementations of, well, second price auctions and generalizations of that, as well as posted price auctions. A lot of works have delved into the foundations of this and found equivalent definitions, and it's also inspired some really cool work restricting this definition, vastly generalizing it, leading to interesting questions about revenue maximization with these type of obvious agents. But the relevant work for the talk today is these works on OSP matching mechanisms. There's been work on matching with single peaked preferences, Pareto optimal matching mechanisms, and a very similar paper to this one completes a classification for top trading cycles. But the most relevant paper for today is this paper by Acyclic and Gonczarowski, which also studies OSP stable matching mechanisms. So we're going to need to spend a good long while reviewing this AG paper. So for historical context, this was actually the first paper to follow up on Lee's original definition. The first draft was in 2015. The question they ask is, when are stable matching mechanisms OSP? And their partial answer is sometimes, but usually not. The typical stable matching mechanism, there's no way to implement it in obviously dominant strategies. But they left open the question of precisely when stable matching mechanisms are OSP. This question was open nearly since the definition of OSP came out, and my paper answers this question. The answer is intuitively almost never. So rarely, peeking ahead a little bit, it's so rare that these mechanisms are OSP that all OSP mechanisms can be built out of 2x2 or 3x3, very simple and small OSP mechanisms. Okay, so let's take a tour through the OSP instances of DA, which are constructed by Acyclic and Gonczarowski. And even though sort of the interesting part of both their paper and my paper is when you can't OSP implement it, we're going to focus on when you can for concreteness during the talk. And okay, one remark I want to make is formally the question is, for which fixed priorities is DA with those fixed priorities OSP implementable? This is what the question formally means. And if you're looking for OSP stable matching mechanisms by some standard theory on strategy proof stable matching mechanisms, you can look just at DA without loss of generality. All right, so here's one thing you can do. If every priority list is exactly identical, say A, B, C, D, then just thinking about DA for a little bit, you can see that you can just match agent A to any of the positions 1, 2, 3, 4 that they want, and then proceed and let agent B match, and then C, and then D. So DA is exactly serial dictatorship with these priorities. So that's one case that's OSP. You can generalize this significantly. AG generalizes this a lot, and we'll kind of think of it as tweaking this serial dictatorship to get a little bit more rich. So here's an example of what is called acyclic priorities. These are nearly aligned like the previous case, but you are allowed to flip adjacent agents. And these flips do have to be non-overlapping. So that's what these just dashed lines mean. AB is always ahead of CD, which is always ahead of E, but among A and B you can flip, among C and D you can flip. Again, thinking about DA just a little bit, it's not too hard to see that you can proceed to implement this by first matching A, B, committing to it, then matching C, D, committing to it, and then E gets the leftover in this case. So this is a lot like a serial dictatorship. It just goes by two, really. And the nice thing is that it turns out that matching two agents according to DA is actually always OSP. And basically, there's only one way to do this, and let's call a mechanism that does that two-trader. Okay, let's look at one example for a little bit. So here is a diagram of how you can match A and B to their favorite positions, where clinching means you permanently match to whatever you pick among the set that is clinchable for you at this node. And if you're not clinching, you're passing. So let's briefly say why this correctly matches A and B. Well, A can definitely get 1 or 2 if they want. B can definitely get 3, 4, or 5 if they want. If A wants 3, 4, or 5, then, well, B could already get 3, 4, or 5 if they want, but they can also get 1 or 2. Because if they want 1 or 2, then they just won't collide with A at all. They'll just both get their favorites and go on their way. So B can clinch anything here. That basically tells you why this correctly computes this. Let's also mention briefly why it's OSP. I won't say exactly formally why this is, but intuitively, so if A should pass in hopes of getting something in 3, 4, 5, this is the only sort of non-trivial case because A acts twice along that branch. But there's 2 cases. Maybe B takes something in 1, 2, and then A can just feel free to take their favorite in 3, 4, 5. Or maybe B steals their favorite in 3, 4, 5, but then 1, 2 is still available. So A sort of obviously never regrets not clinching 1 or 2 because if they fail to get their favorite, 1 or 2 will still be available down here. All right, so this is basically the only 2x2 stable matching mechanism, and it is OSP, and we call it two-trader. After you match A and B, you can proceed to match C and D by the same type of thing, and this is the sense in which, I mean, there's only one two-trader mechanism. You just kind of tweak the clinchable sets a little bit. That's the only difference you need to make. So you can recursively continue to match agents in an OSP fashion. AG also provides an example where priorities are cyclic, but things are still OSP. It's still a fairly aligned case, but you can flip overlapping agents in this pretty specific way. And I won't talk much about how this mechanism works, but one trick that it uses is if A proposes to 3 in DA, if that's their favorite, then we automatically know that C can never get 3. And this is something that the mechanism harnesses to reduce the number of possible outcomes for C and make the mechanism simpler and more obvious overall. So mostly black box this mechanism for the talk, just call this mechanism the 3-trader mechanism. All right, now we finally know enough about these mechanisms to state the main theorem. It's actually that every OSP stable matching mechanism can be constructed out of 2-trader and a very simple generalization of 3-trader. So a couple of clarifications are in order. What does constructed from mean? Well, we already saw an example of constructed from in the case of acyclic preferences, where we just did 2-trader and then another 2-trader and then another 2-trader. Here, you can also put in a 3-trader. So the right way to generalize it to having a lot of possible positions is actually to make all of the priority lists identical except for 2. And in the final 2, we have this overlapping flip that I was highlighting earlier, and this defines a 3-trader mechanism among C, D, and E. And one important thing to note is that no agent appears in distinct submechanisms. So this is actually a very strong definition of constructed from these little pieces. And to explain a little more what a simple generalization is, still it must be the case that all priority lists coincide except for 2. And still it's the case that the mechanism matches agents 3 at a time. But these overlapping flips can be a little bit longer. One of the agents can start flipping at the second spot and every adjacent spot on, and one of the agents can start flipping at the first spot and every adjacent spot on. And this is the only thing you can do. You can generalize this, but there's nothing else at all, no other configuration of flips. So I'll just spend one slide on what is actually the hard part of my paper, is proving when things fail to be OSP. So this does involve a lot of work. It probably would be impossible to present in any reasonable way in actual slides, but you just prove that a whole bunch of priority lists fail to be OSP, all of these lists specifically. And then you do some very careful pattern matching to classify those priority sets which don't contain any of these sets as a subpattern. And this implicitly uses this sort of known lemma that if any subpattern fails to be OSP, then the priority list as a whole fails to be OSP. So these are the techniques. Revisiting this main theorem, so the way I originally stated it for concreteness was that there are only really two non-trivial stable matching mechanisms that are OSP, this 2-trader and 3-trader. But the proof structure actually affords another dual classification, which is that any non-OSP priority structure contains some irreducible non-OSP thing, which comes from this particular finite list of non-OSP priorities. So there's these two dual ways to understand the result. There's these core building blocks of what is OSP, and there's these core building blocks of what fails to be OSP. And lastly, we saw several examples of cyclic but OSP priorities, and an equivalent way to state the main theorem is that these are the only cyclic but OSP priorities, these extremely specific patterns. So just to wrap up, this was pretty startling, I thought, when I first proved this. It is sort of amazing that all of the OSP stable matching mechanisms were already known in AG. They can't really do anything at all except what was already possible on 2x2 markets and 3x3 markets. And in particular, an agent can only interact with OSP stable matching mechanisms in these very simple ways at most 2 times. So we can conclude that the tension between obviousness, at least in the sense of OSP, and expressiveness, diversity of priorities, is extremely high for DA. And extrapolating a bit, we might even conclude that almost no part of DA is obvious in this sense. Thanks.